The objective of this lecture is to understand how integration works, and for the purpose of theory, I have taken this extract from NCERT class 12th math book, and at the first glance itself, it appears to be very complicated and convoluted. So let's try to figure out how to understand this a really simple concept more crisply, more clearly. So when we talk about integration, the first thing that comes to mind is area under the curve, and it's a very important concept. So before we understand what integration is all about, let's try to understand this concept of area under the curve. And to exemplify it, I'll take a very practical problem. Let's assume that there's a man who's running at a speed of 2 meters per second, and we want to know his distance after 10 seconds. Now this problem can be plotted in terms of a plot where x-axis is time and y-axis is the speed. And in this problem, the speed of the person is constant, which is what is depicted by this blue line. So if we have to figure out how much distance he has covered in 10 seconds, then we follow this algebraic expression, speed into time. And obviously, speed is 2 meters per second multiplied by 10 seconds, it will be 20 meters that the person has covered in 10 seconds. But instead of looking at this problem from algebra perspective, let's just look at it geometrically. Let's try to concentrate on this rectangle. The breadth of this rectangle is nothing but the speed, and the length of this rectangle is nothing but time. So when we are multiplying speed by time, we are actually multiplying breadth of the rectangle with the length of the rectangle. And in geometry, we've been taught that when we multiply breadth of a rectangle with its length, then effectively we are calculating its area. And that's how this concept of area under the curve originates from. And this is a very, very important concept. Let's try to solve this problem in a slightly different manner. So instead of considering the entire 10-second duration, let's split this axis, the time axis, into interval of 1 second, and each 1 second is represented by a variable called dt. So this is how it will look. So what we're trying to do right now is take a very small chunk of time, which is just 1 second, which is defining only this much length of the rectangle. And then at this point, we are calculating the value of y, which is 2. So the area of this small rectangle is nothing but 1 into 2. And then in the next step, we are again going to increment this small dt, which is 1 second. And at that point of time, that is at 2 seconds, the value of y is 2 meters per second. So this area again for this rectangle is 2. And we continue to repeat this process over and over again until we have reached the 10th triangle. So this table depicts the same exercise. This column, the first column, dt column, is the time slice. Each time slice is 1 second. And this column is y-axis, which is depicting the speed. So at every time increment, the speed remains constant. At the first increment, it is 2, then again it's 2, and so on and so forth. So that's why so many 2's are appearing in this column. And then what we are doing here is that we are calculating the areas, and we are calculating the running sum or the cumulative sum of all the small rectangles that we are calculating. So the first rectangle has an area of 2. The second rectangle also has the area of 2. This 2 gets added with the first one, so we have 4. And then again we calculate the third rectangle area. It is again 2, and we add the 2 to the previous 4. And this is a running sum. When we add all the rectangle areas, small rectangle areas together, we come to the final result of 20. Now, why are we doing this? Why are we solving this problem in this manner? It will become clear from this slide. Our approximation or our assumption that area can be calculated using rectangles, it starts to fall apart if the speed or the curve is not a straight line. If it is something other than a linear line, then you can clearly see here that approximating this dark green area under this exponential curve using rectangles, it starts to fall apart. It is overestimating the area, and that overestimation is happening because this dt is a very large interval here. So what can be done? So in this case, there are 10 rectangles which are trying to approximate the area of this exponential curve. and here we have 100. So now you can see that the same curve, the same area under the curve can be approximated better if the length dt is tending towards 0. The overshoots here are quite less, those they are still there. If you increase this dt from, if you make it smaller further, then these overshoots will also start to disappear. And then once we have no overshoots, no major overshoots happening here, then we calculate all these small areas using rectangle approximation, which more or less now fits in, and our end result of area calculation is more precise. So in the summary, this small dt results in a better approximation of area under the curve. So if you have understood this concept of area under the curve, then we are ready to understand this very complicated looking formula. It looks complicated, but it's very, very simple. Let's dissect this formula. So this small dx is nothing, it's a small increment in the x-axis, equivalent to dt, what we have just studied in the previous problem. And this dx has to be small so that the approximation that we have made, that area can be calculated using rectangles, that stands valid. Otherwise, if this dx is too large, then that assumption starts to fall apart. This dot, which is often missing in traditional notation in integration, I have specifically put it here to show that this is nothing but multiplication of two quantities, two numbers, dx with fx. Now this component is just the y-axis, y value, in response to the increment made on the x-axis. So in the speed problem, this was always 2 meters per second. So make a small increment on the x-axis and then calculate corresponding value on the y-axis, and then take these two numbers together and multiply them. So that will calculate a small rectangle area, and then what you have to do is you have to implement a cumulative adder. So this symbol here is nothing but it's a running sum, it's a cumulative accumulator, and it is basically carrying forward a running sum of all the areas of the small rectangles that we are calculating. Now if you look at closely, this fx is nothing but the breadth of the rectangle, and this is the multiplication sign, the dot, and this dx is nothing but the length of the rectangle. And when we multiply both of them together, we are computing the area under the curve of a small rectangle, and then we are going to continuously add it in a cumulative summer or cumulative adder, so that the complete area under the curve is computed. So it's as simple as that. There's nothing more to integration. It's such a simple operation. It just contains only two maths operation. One is multiplication and the second is addition. Now we'll try to code this formula in Python, and it will give us much better clarity as to what is going on behind the hood. So in this section, we will try to implement integration using first principles, and we will use Python for that. We will take a cosine function and we'll try to compute its integral using first principles. So this is that familiar JupyterLab environment that I had shown to you in the previous lecture, and I've imported some important libraries to get integration implemented. Alright, so let's get started. The first step in integration, as we discussed earlier, is to define the small step dx, which is the incremental step on the x-axis, and it has to be small. So let's define it as 0.01, and now we have to compute the entire x-axis so that we can feed these numbers to the cosine function to generate the y-axis. So firstly we have to have a start of the x-axis. So let's start with minus 2 pi, and we have to have some stop of x-axis. So let's just copy this, and so what this piece of code is saying is that my x-axis is going to start from minus 2 pi and it will end at plus 2 pi. Let's generate the numbers. For this I'll use a function called arrange. So how it function is that I have to give it a start number, I have to give it a stop number, and I have to then tell that between these two numbers what will be the incremental steps for the rest of the numbers. So that's how it looks. Let's just print these numbers and see how they look. So there we are. We have from minus 6.28, which is minus 2 pi, to plus 6.28, which is plus 2 pi. We have many numbers in between, and each of these numbers have got an increment of 0.01. So now let's calculate how many such numbers have been generated. So there are 1257 such numbers. This is now our complete x-axis. Moving forward, let's generate the y-axis, which is our function fx. So let me define a variable fx, and I will use numpy's cosine function for this, and feed our entire x-axis to this function, and then I will print these this y-axis and see how it looks. Yeah, so this is what is the y-axis, or the cosine of the x function, and we can see that for minus 2 pi cosine is 1, and also for plus 2 pi cosine is 1, and in between there are 1257 numbers. So more or less we are on the right track, but let's check it visually also. So I will plot our x-axis, and on that y-axis we have this function, and let's do a quick check whether we are on the right track or not. Yeah, so this is pretty much it. We have x-axis which is varying from minus 2 pi to plus 2 pi, and we have a cos function which is looking very neat between 1 and minus 1. So this was a quick visual check that we are on the right track. So now comes the part where we have to implement the integration. Before we do that, as I discussed in the previous section, integration is nothing but a cumulative adder. So let's see how it is implemented in Python. It's just one line code. To prove that to you, let me just generate a sample list of numbers, a dummy list. Let's say 1, 2, 3, 4, 5. As I discussed earlier, that cumulative summer is nothing but the running sum of the number series. So I will generate a cumulative sum of this series, this array, which is very simple. You just have to use a function called CumSum and pass on these numbers to the function, and let's see both these series of numbers, both the arrays. There we are. So our original numbers were 1, 2, 3, 4, 5, and the running sum is 0 plus 1 is 1, and then the next number is 2, 2 plus 1 is 3, 3 plus 3 is 6, 4 plus 6 is 10, 5 plus 10 is 15. So definitely a cumulative adder has got implemented, and we are going to use this function to implement our integral. So this was a quick tutorial on how to go about using this function. So what was integration? Integration was nothing but a product between fx and dx with a running cumulative summer on the entire this function, this expression. So let's just implement it. So I'm going to declare a variable called integral, and what I'm going to do is I have to have a cumulative adder, and in this adder I'm going to pass on my function fx, and then I have to multiply it by dx as is given in the integration formula. So this one line of code is sufficient to implement integration, and as I mentioned also, that integration is nothing but only two operations. One is this multiplication, and the second is running adder, nothing more to it. So let's print these numbers and see how they look. So we have definitely got a series of numbers here, and we will definitely plot them to have a visual appreciation of what's going on. The theory says that the integration of cos, or integral of cos, is sine. So ideally speaking, this number series that has got generated should be a sine wave. Let's see if it is if it's indeed a sine wave. So let's do a quick visual plotting. We generate x-axis. On the x-axis we are going to generate our function, that is y-axis. I want this plot to be in magenta color, and I want the label of the plot to be cos x. So let me just quickly check whether this is functioning or not. Yes, it indeed is working. So I don't want these dashed lines, I just want a solid line. Yeah, so there it is. So I've plotted my original function, and now I have to plot its integral. And if the integral has worked properly, if this algorithm has worked properly, then it should look like a sine wave. So here I'm going to plot the integral, and let's plot it in red color, and let me just change its label to integral of cos x. and let's just plot that. Well, it looks like a sine wave has got generated. Let's just try to improve this plot. So not only I'm going to generate the integral of this cos, I will separately generate a sine function so that I can validate whether it's indeed following the sine pattern or not. So for that, I will generate another plot, x-axis, and now on my y-axis I want the sine function to validate if my integral is correct or not, and I want this to be in black color, which is signified by k, and it has to be a dashed line, and I want a label to it, which is sine x. Alright, and I want my legends to show and my plot to show. So let me just quickly plot it. There we are. So this magenta is our original function cos x. The red, which is now overlapped with black, is the integral of cos, and as the theory says, integration of cos leads to sine wave. And as a double check, I have plotted a sine wave on top of it. Both the integral and the sine are matching, which means our integration algorithm is working correctly. And there's nothing much to this integration algorithm. It is just one line of code, nothing much, which is this. So integration is nothing but a cumulative sum of small rectangles, small areas that we are calculating using this particular formula. That's it. There's nothing more. And now let's just do some more improvement in the plot. So I want the grid lines to show. So now you see that a grid appears. So we have a 0 axis going up here, and we have another 0 axis. I want those 0 axis to get highlighted. Horizontal line, and I want color to be black, and I want line style to be dashed. So this will plot a horizontal line on the 0 axis. Here it is. And I also want a vertical line, which is just a repetition of this code. I just have to change this to vertical line, and there we are. We have a vertical line. Also, I need to give titles to these axes, x-axis and y-axis. So I will use this function and give x-axis its label, and I will just copy paste this code and use it for y label, y-axis. And there we are, x-axis and y-axis, they are showing. I want a title to this plot. I will name it cos x and its derivative. So there it is, cos x and its derivative. So how quickly we have been able to verify the theory in code. We just about spent some 20 minutes on it and very few lines of code, and we can very clearly see that learning maths this way is more beneficial. And as I mentioned last time also, that once your code is functioning fine, then you can do a whole lot of experimentation. For example, you are not restricted only to, say, cos function. You want this to be, say, an exponential function. So then all you have to do is, the theory says that integration of exponential function is exponential function itself. So let's see if it's happening. There we are. Both the lines are overlapping, so we can't see. So integration of exponential function is an exponential function. We can quickly validate it. We can play around with this code and validate so many other functions that we learn in the math book. So in summary, that complicated looking integration that is taught in school books is nothing. It's just one line code, which is cumulative addition of small areas that we implement using this expression. And you can, once you are in any kind of programming environment, you can plot them, you can see how they look, how the original function looks, how the integration of it looks, and you get a much better understanding of what's happening behind the scenes. Thank you.